Okay, so problem 1 states sparks occur when an electric field in air exceeds 3 times 10 to the 6 newtons per coulomb. This is because free electrons normally present in air are accelerated to such high speeds that their kinetic energies will overcome the potential energy holding other electrons to atoms. When those electrons rearrange themselves after such a collision, a flash of light is emitted. Let us suppose that the work done on an electron must give it an energy of 3 times 10 to the negative 19 joules to cause this ionization. How far does an electron involved in making a spark travel through the air before it collides with an atom? Okay, so that's a lot to digest. So before we begin, let's just look at what the problem really gives us. So it tells us that the electric field we need has to be 3 times 10 to the 6 newtons per coulomb. Newtons per coulomb. It also tells us that the energy we're dealing with has to be 3 times 10 to the negative 19 joules. Cool. So this is what the problem statement tells us. This is the information it gives us. What are we looking for then? How far does an electron involved in making a spark travel through the air before it collides with an atom? What we're looking for is some distance d. So what equations do we have for this then? So there is an equation relating electric field to distance. This is the electric field is equal to negative the electric potential V over D. I believe in lecture you went over this equation instead using delta V over delta Z. This is kind of the form we're going to use here. It's essentially the same thing, right? A change in potential between two locations that are at some distances away. Yeah, I'm just going to scrap some of that. Okay, the other equation we have is for electric potential energy is equal to the charge or some charge times the electric potential it's in. And so the quick thing I want to make note of here is this U, as I mentioned just now, is electric potential energy. Electric and energy is the big term here, where this V is electric potential. Why would physicists choose to name these things something so similar, even though we know it's just going to confuse you? Good question. No idea. But you can know that the electric potential is related to the electric potential energy that a charge will have in that electric potential just by multiplying the charge Q by the electric potential. Okay, and so with that in mind, we're looking for D. So if we had the electric potential that this electron is in, we could actually just plug in for this equation, plug in for the electric field, and solve for D. However, of course, we don't have the electric potential. We could solve for it by plugging in for the charge of an electron, which of course is just negative 1.6 times 10 to the negative 19 joules. We could plug the charge of an electron into the second equation, solve for the electric potential, and plug it back into this one. Instead, I would rather combine these two equations so that I only have to do one calculation at the end of the day. So that's what I'm going to do. I'm going to take this first equation, E is equal to negative V over D, and solve for that electric potential by multiplying negative D over to the other side. This will get us the electric potential is equal to negative ED. And now we can plug in this electric potential is equal to negative ED into this equation. Right, so if we have U is equal to QV, we now have U is equal to negative QED. Awesome. So we have U, Q, and E. All we have to do now is solve for D. So solving for D, we divide both sides by negative QE, and we're left with the distance this electron moves through is equal to the negative of the electric potential energy divided by the charge of an electron over the electric field. Okay, so just go ahead and plug all these values in. So we're going to have negative 3 times 10 to the negative 19 joules divided by the charge of an electron, negative 1.6 times 10 to the negative 19 coulombs, times the electric field, which is 3 times 10 to the 6 newtons per coulomb. Let's check out our units real quick. So we're going to see in the denominator here, the coulombs cancel out. Then we also have joules divided by newtons. But a joule is just a newton meter. And so those newtons will cancel, leaving us with meters, which is a unit for distance, which is perfect. It's exactly what we're looking for. So doing all this, we should arrive at a final answer of 6.25 times 10 to the negative 7 meters. Which if you wanted to, you could convert to something a little more pleasing to the eye. This would look nice as 0.625 microns or micrometers. You don't have to do this, of course. You could always leave it in like scientific notation. That's perfectly valid. And in fact, I would probably recommend keeping it this way, unless specifically told to convert to another unit. If only because every time you do something else, you just introduce a spot where you can make a mistake. And so why do that if you don't have to? But yeah, that's problem 1.